are facing some problems with the connection with the West. I think we must go on with the presentation from the research centers, and then when we connect with the Professor Stefan, Alexander, then we will stop the presentations, and well, we'll try to do this in the best way that we can do it. So the first speaker is Manuel Soto from CSEC. Can you come, please?
Okay, good afternoon to everyone, and thank you for the introduction. So it's a pleasure to be here and to participate in this research summit and to present some of the work that we are carrying out at the CSECO and Department of Chemistry. Today in this presentation, I'm going to show an overview of the different research lines that we are developing, which are mainly focused on the design of new electroactive porous frameworks, such as metal organic and covalent organic frameworks for different applications in electronics. So we are working in the field of molecular electronics, and what we do is basically to use molecules as the basic components for the fabrication of electronic devices. So during the last decades, the molecular approach to material science has become a very promising research field for the future generation of electronic devices at the nanoscale level. The main relevance of these molecular materials is mainly due to the almost infinite possibilities for tuning their physical properties, such as electrical, optical, and magnetic properties, by using simply conventional chemical synthetic methods. So the high versatility and tunability of molecular chemistry offer excellent opportunities for the design of new functional materials for a wide range of applications. These molecules can be considered as the basic constituents or building blocks for the fabrication of functional materials or complex devices, following the bottom-up approach, which is based on the self-assembly of these molecules via intermolecular interactions. So this is in general a versatile, easy, and low-cost process, becoming attractive from a technological point of view, and the functional materials can show specific properties, desired functionalities, and find several applications in different fields, for example, electronics, optoelectronics, or energy storage. Today, I will focus on two different types of porous frameworks. The first, metal organic frameworks, or MOF, which are constructed from organic ligands and metallic nodes, leading to an immense chemical and structural diversity of 2- and 3-dimensional structures. So this is an inorganic organic hybrid material, whereas covalent organic frameworks, or COF, are purely organic material, okay? And the organic building blocks are linked via strong covalent bonds, leading to a highly stable material. And also, depending on the geometry of the starting building blocks, we can obtain a huge diversity of topological structures. In both cases, we can find multiple applications, for example, in gas storage and separation, catalysis, or energy storage, whereas stability, crystallinity, and scalability are the critical parameters toward industrial applications. Besides their inherent porosity, MOFs and COFs can incorporate electronic functionalities from their building blocks, which is of high interest towards implementation in electronic devices, and can show specific advantages such as the high versatility, chemical and structural versatility, porosity, which is especially interesting towards energy storage applications, and finally, the possibility to tune their physical properties by post-synthetic modifications. So indeed, in the last few years, we have seen several examples of MOF and COF-based devices, such as sensors, transistors, or capacitors. At CSECO, we are mainly interested on the incorporation of different electroactive building blocks, which have been widely studied in organic electronics, for the construction of electroactive MOFs and COFs. And then we use these kind of materials for the fabrication of different devices, such as batteries and supercapacitors, field effect transistors, or light emitting devices. So today, I will focus on the use of electroactive COFs as electrodes for the fabrication of batteries. So lithium-ion batteries are probably the most promising energy storage device due to their extensive use in portable electronics and towards the development of electric cars. So basically, lithium-ion batteries are based on a graphite anode and a transition metal oxide cathode, which are separated by an electrolyte, allowing the exchange of lithium ions during the charge and discharge processes. However, the cathode material, transition metal oxides, present two main problems. The first one is the limited energy density, and the second one, and probably the most important, is the reduced resources availability, especially for cobalt and lithium in the future. So there is a high interest of designing new and more sustainable electrode materials. In this direction, organic materials, and more in particular, covalent organic frameworks, have emerged in the past few years as promising electrode materials due to their high stability and insolubility in electrolyte, the order porous channels allowing to increase the ionic diffusion, and finally, the possibility to introduce multiple red oxides to increase the capacity and thus the energy density of the batteries. However, there are two main challenges for the design of COF-based electrode materials. The first one is the usually low electrical conductivity. Also, some strategies have been established in the last few years to increase the charge transport in this kind of materials, such as the use of electroactive building blocks, increase the conjugation through the framework, and also to control the orientation and morphology of these materials. And the second one is the processing. So COFs are usually two-dimensional materials and can be exfoliated in the same way that we exfoliate graphene from graphite. Okay, so it has been demonstrated that by exfoliating COFs through different techniques, these exfoliated COF nanosheets show an enhanced diffusion and then an improved electrochemical performance of the batteries. So these are the two main challenges that we're working with. And I would like to finish showing a recent example that was published in Nature 1 month ago. It's not a COF, but it's an organic electrode based on polypeptides functionalized with two different types of electroactive organic molecules. So these are redox active, to be used as cathode and anode. And one interesting thing of this material is that can be stable during the battery operation, during the charge and discharge cycles, and can be degraded in acidic conditions, so it can be recycled. This is I would like to highlight this material because it's important to design new materials that can be more sustainable and recycled. And just to finish, the Seco Aveiro Institute of Materials is the largest and best-rated material science and engineering institute in Portugal. We are more than 500 chemists, physicists, and materials engineers. And thank you to all of you for the attention.
Thank you, Manuel, for these interesting lectures on the MOFs and their applications and the hot topics that we are facing today.
Thank you.
We need to go on. Nuno Lau. No, it's not there. We move to the tema. Yeah.
Thank you very much for your presentation. I'm Marcos Santos. I'm assistant professor in the Department of Mechanical Engineering, and I would like to thank the opportunity to be here to presenting my research with the research I'm conducting with my research team. My research team is not only comprised members from TEMA, but also from CISECO. So, namely Andre Coquin and João Pirão. Well, today my talk will be focused on new trends in electromagnetic energy generation. Well, firstly, I want to say that TEMA is a research center of mechanical technology and automation. Is mainly organized into main mobilizing projects. The first one is related to sustainable manufacturing solutions. The second one is related with technologies for well-being. Well, this organization, or this second topic can be subdivided in two main ones. The multi-scale technologies for devices and medicine, environment and energy, and the second one, innovative technologies for smart cities. So this work is mainly related to the second mobilizing projects, since we are developing technologies such that we can contribute towards the clean safety, as well as to good health and well-being. The first one that is related with clean energy, we want to reduce new renewable energy sources by projecting large-scale power systems. And we also want to develop smart medical devices using small-scale power systems using the same architectures. Okay. So, for instance, for the first scope, large-scale power system can be used for harvesting ocean energy, for instance. And another research we are conducting is to developing smart bioelectrical bone implants, and these require small-scale power systems. Well, what are the problems about electromagnetic energy harvesting? Well, nowadays they require complex mechanical systems, which is the reason because they require high maintenance costs and high production costs. Besides, they are unable to ensure performance adaptation to varying mechanical vibrations. So the solution we are working on is a solution based on mechanical levitation architectures, in which we have a container, a lowered container, in which levitation magnets moves in relation to outer coils around the outer surface of the container. And so this is a very easy, non-complex, and low maintenance solution. Well, this is an excellent idea. We think so, but these kind of architectures have relevant problems. We are trying to solve. Namely, the first problem is about the performance strongly dependent on frequency excitation. So it behaves like a resonance circuit. And so if the external excitation changes, the performance of the generator decreases significantly. The second problem is about hysteretic behavior. So when we are talking about increasing frequencies or decreasing frequencies, the performance will be different. So to try to solve these problems, we are working on two different approaches, but both are based on self-adaptive structures. The first one uses magnetic levitation system to generate energy, but it uses instrumentation, namely processing systems, and a step motor and accelerometer, such that we can change the properties of the electromagnetic system, such that it can track the changes in excitation frequency. So the adaptation strategy is to change the generator length as a function of amplitude of frequency of mechanical excitation. So our purpose is to use a motor inside the electromagnetic such that we can change the generator length such that it can adapt by itself. Well, we are able to identify the patterns that correlate both frequency, amplitude of the excitation with performance. And so we have the basis to determine or to identify which is the optimal length, generator length, such that it produces the optimal outputs. So with this strategy, we currently obtain power gains higher than 30%, which is very good, very good performance for this type of generators. Yeah, and this considering the power consumption of instrumentation, because we add instrumentation. Instrumentation consumes energy, but we are gather together energy, and the confluence of these two energies allow us to obtain power gains. Okay. The other strategy is, instead of using a step motor, because it consumes a lot of power, using a commutation system. So the main strategy is to implement switch the coils on and off, between on and off several coils, such that the performance can be enhanced. And so we have already identified a strategy that consists on the electric connection of 2 or 4 coils, dependent of the frequency amplitude of mechanical excitation. And with this so simple strategy, we obtain power gains higher than 25%. Nowadays, we are working in other switching strategies, and we hope to increase these power gains up to at least 50%. Okay. So ongoing research, our ongoing research is focused on to bring artificial intelligence to energy harvesting, which is a radically new idea inside energy harvesting. Now inside energy harvesting, but not for optimization, but for tuning, artificial tuning. And so our goal is we need artificial intelligence to make accurate predictions of the mechanical excitation, such that the decision making of switching or enable dark quenching mode can be optimized. So this is the ongoing research that we are conducting now. Thank you for your attention.
Thank you. So I would like to thank Manuel and Michael for helping us to start. Now we going on with our expected lecture from Professor Stefan Alexander. We are now connected with US. I will say only 2 or 3 words about the Professor Stefan Alexander. It's a theoretical physicist specializing in cosmology, particle physics, and quantum gravity. So he received the BSc in '93, and then the PhD from the from the Haverford College in 2000, from the Brown University, sorry. Then it was postdoctoral fellow at the Imperial College of London and Stanford University. He has previous positions in Penn State University and Dartmouth and others. Now he also explore the interconnections between music, physics, mathematics, and technology. So I think it will be a great opportunity to see how we connect physics and music, and it will be very, very happy to listen to Professor Stefan Alexander. I would like to thank Professor Alexander to accept our invitation and to share with us some of his thoughts about these interconnections.
Okay. Can everyone see my screen, or let me know what you need of me on my side?
Please, Professor, can you go ahead, please?
Okay, can you hear me and can you see the screen?
You are mute.
Oh, I'm mute. Okay, sorry. Hold on a second. Oh, can you hear me? Hello?
Yes.
Can you hear me? Hello?
Yes.
Okay. All right, good, very good. Okay, and can you see the screen?
Yes.
Yes.
Okay, so my partner speaks
Hi,
Portuguese.
can you try again, please?
Can I? Hello?
People in the Zoom session can hear, but I guess in the room they cannot for some reason.
Okay.
Okay, I think we may try. Hi.
Okay, I can hear Vera, and I can hear people in the room there. But can everyone hear me?
Yeah, we can hear you with some delay, but let's try another thing here. Just a second, please. Can we try again, please?
Okay, yeah, can you hear me and can you see the screen?
Hi. Okay,
Hi.
thank you very much.
Okay, so the answer is yes. Everyone can hear me on all platforms.
Yes, we can hear you.
Okay, very good. All right, so to the Ben, and it's a great pleasure to be speaking at this wonderful event. Just to let you know, this is much of my talk is based on this book, The Jazz of Physics, and this book, I'm very grateful and honored that the book was translated into Portuguese. In fact, I was very happy to know that the first country to acquire my book was Portugal. And I'm very enamored and very endeared. You know, as you very well know, also my very first postdoc, you know, what opened my career was João Maguiejo, the great Portuguese cosmologist, was the person to hire me at Imperial College, and I wouldn't be here if it wasn't for João's you know, support and in my career. So expect me to be in Portugal as soon as things clear out, especially to check out your beautiful country. My talk is going to basically is based on a lot of things that I've been, you know, exploring over my, you know, the last 15 years of my career. So let's just begin. You know, it's my way of basically combining how I see music and my science merging together. It's certainly not a unique way of doing that. And so let's just begin. Oh, actually, it just occurred to me that Let me just begin again. So when I was younger, growing up in New York City, I was very much, on the fence about whether or not I was going to become a scientist or a musician. And, young people, we take a lot of input, right, from society, from the media, from our teachers, from our parents. And back then, the messages I was getting was, it's cool to be a musician and not cool to be a scientist. I grew up in a musical family, and so a lot of internal pressure was mainly to pursue music. And at that time in the Bronx, New York, hip hop music was very commonplace. It was a place where hip hop was invented. And I was hanging out in recording studios as a teenager, and one way of staying out of trouble. And then I came across, so that struggle, conflict of whether or not I should be a musician or a scientist, sort of remained with me throughout my career. I mean, even though I became a professional scientist, in the formative years, it was still not clear whether or not I should pursue the path of a musician. But something changed when I ran into the music of this artist, Rakim. And he was known to be, in my era, in my time, the greatest rapper, or MC on the scene. And if you see that his line here, that's what I'm saying. I drop signs like a scientist. My melodies are cold. The very next episode has a mic off in the store and ready to explode. I keep the mic in Fahrenheit, freeze MCs to make them colder. My listener's system is kicking like solar. So what does that have to do with a 14-year-old kid in the Bronx? Well, back then, a lot of rappers were talking about other matters, like being, maybe you're a better dancer than somebody, you can rap better than somebody. But here is the top rapper making references to science and scientific matters. And that, he was a role model. And the fact that he was talking about science made sort of like, I don't know, it inspired me to continue down, that it was okay as a young person to pursue the path of the science. It was okay to identify with that, because this role model in his own way was identifying with that. And I think that's a very important lesson for those of us who engage with younger people and who are teachers or who may bring people into our labs. It's very important that we keep in mind kind of like maybe in what they're going through and how they identify with the scientific pursuit, and to realize that there are many different ways that we can identify with being a scientist. And this was one way, right? Another inspiration was Albert Einstein, and he remained an inspiration to me because he showed that you can kind of be your true self and be a scientist, and be a great scientist. And in fact, being your true self actually is linked with being the best scientist that you can be. And of course, where my interfacing with music and science really congealed, and I'll talk about it, kind of like the basis of the rest of what I'm going to talk about is related to John Coltrane. He has international acclaim, so I'm sure everyone knows who John Coltrane is, but he's known to be probably like, one of the greatest, if not the greatest, jazz sax player and composer and innovator in history. And what we're looking at here is a diagram that he drew. So in a nutshell, I mean, my book covers this in some detail, but Coltrane he wasn't just playing music. He didn't think of himself simply as a person that would get on stage and play music for people. He wanted to transform people's consciousness, he believed that his music was interconnected with the happenings of the cosmos. So he was deeply into cosmology and philosophy, and everything that he can get his hands on about Albert Einstein in particular, he would read, okay? So back then in the 50s and the 60s, there wasn't much opportunities for an African-American person to pursue the sciences, okay? And, Coltrane basically took that out on his saxophone. So what you're seeing here is this diagram that Coltrane made, where he is, he basically is trying to come up with a similar system for what Albert Einstein did for space and time. So Albert Einstein, remember, his idea of space and time was that space and time was about a structure, right, based on symmetries and the fact that when light moves through space and time, the fact that light moves at the same velocity, regardless of what perspective you look at that light from, meant that there's an underlying symmetry, an underlying invariance. And this diagram that Coltrane drew here was a way of basically trying to come at the same type of idea of invariance and symmetry for a musical system that he was developing. That system later on became known as this album that he did called Giant Steps. And so that kind of, those are some little things that inspired me to, as a person that was very much involved and still interested in music, as well as pursuing a professional career as a scientist, you know, to sort of figure out how those two worlds that were separate for me spoke to each other. Now, in the interest of time, I'm going to skip over some other things, but very quickly, when I went to Imperial College to work with Joao, I also befriended a musician named Brian Eno, who many of you know produced various people, right? U2 and to name a few, Coldplay. And he was a musician that used a lot of ideas. He liked hanging out with scientists and mathematicians because he would actually take your ideas and bring it into his music, even though he wasn't an expert. So that inspired me to do the reverse, to say, well, okay, I'm here as a postdoc pursuing my research at that time in string theory and cosmology as a theorist. And the question I had for myself, inspired by Brian Eno, was, can I just boldly and shamelessly, you know, take ideas from my music and try to use that as one other tool? So just you know, as a theoretical physicist, we have to come up with new ideas. We're trying to come up with models to understand the physical universe, a physical system, you know, quantum physics, whatever the system that we're studying, we are trying to basically, you know, understand certain mysteries, certain, you know, experiments, maybe produce a new model. And we use tools, and those tools usually are based on physical intuition, bringing in ideas from other subfields in physics, computational tools. Sometimes we use computers to do analysis, but also mathematics and, you know, mathematics, geometry, algebra, these are tools. But what I was playing with here was whether or not I can use in my toolkit music and improvisation, since that is very commonplace in jazz, right? So as a jazz musician, you know, one of the things we try to hone and practice and perfect almost is improvisation. So the question is, am I able to use music and in its full glory as a tool, like these other tools, in my theoretical work? I'm going to skip that. And one of the tools and so when we think about tools, we might want to think about language, right? We might want to think about, like, you know, that every tool we use has a system. So for example, if I'm doing mathematics, I might be dealing with a system called algebra, right? And there is, you know, a language there. So in music and in physics, it turns out that there's a common language that both of these systems have. In physics, a lot of we can understand a lot of physics by understanding the physics of waves, or let me call it the language of waves, because the idea of a wave is actually not yet physical. It's more of an idea. And it turns out in music as well, that is also a common language. So what I'm going to do is spend the next 5 minutes talking about the language of waves, and then using that as a portal that will connect the physical with the musical. Now, the physical I'm going to talk about, I'm going to try to spend the next, like, you know, 15 minutes of my time is to try to understand the following question. When we look in the night sky, so we can use, when I teach physics, I make a following and understand about 80 to 90% of all physics through understanding waves and how waves interact, and let's say the logic of waves, okay? And so based on that, we're going to ask one subset, one question that concerns physics. And this is the physics of cosmology. One question we can ask is when we look at the night sky, on a very clear night sky, we see the Milky Way belt. We see the belt of the Milky Way galaxy, which is basically, a spiral motion of billions, hundreds of billions of stars. And we can understand, when we look further out, we see even more and more galaxies, more and more systems of stars. How many? Like, hundreds of billions of galaxies. So what I'm going to show you in the next slide is a computer simulation that agrees with telescopic data of the distribution of galaxies. And the question that we're going to ask, and one of the main questions that we ask in physical cosmology is, what is the physics that gave rise to all these galaxies and stars? And what I mean by that now is that what we're going to see is a pattern. We're going to see a pattern of galaxies that's distributed across space. And we can ask the question, how did that pattern come about? What is the physics that is responsible for that pattern, right? And I'll get to that in the next slide. And what I'm going to now claim is that the way we understand that is through the lens or through the language of waves. And I'm going to give you the answer ahead of time. It's going to be through the lens of sound, not math necessarily in the way that not abstract mathematics and algebra, but actually through the lens of sound. But to understand that, we need to understand a little bit about waves. So what we're looking at here, from the top corner here, from the left to right, is a wave that's moving to the right. And if the wave hits the wall, it gets reflected by inverting itself. And so that's what you see if you look at the ocean, right? Now, it turns out that if I go back to this graph here, and the wave that's going to the, if I look at this other picture here, I have a wave coming, moving to the right, and a wave moving to the left. The idea is that when these waves actually interact with each other, they cancel each other out. That's called destructive interference, right? So the thing I want you to take away here is that when waves come together, they can actually get bigger, or if they come together in a way that where they oppose each other, they can cancel each other out. All right, that's interesting. But that happens when we add two waves together. But if we add, for example, three waves together, what we see in here is one wave. By the way, can you see my arrow?
Yes.
Yes,
Okay.
we do. Yes, we do.
So to the top here, we have one wave. In the middle, we have a bigger wave. And at the bottom here, we have a more wiggly wave. And now if I add these three waves together, the thing I want you to take away is this equal sign means that if these three waves get added together, I get a more complicated looking wave. All right. Now, this is just a fact about waves. Now, there's a fancy word for this. The idea to add these waves together is called related to something called a Fourier Transform, named after the French mathematician. Many of you who are very familiar with this, I make the claim that this is one of the most useful, if not the most useful idea in physics and engineering. Now, this would be trivial if the other, if this was all about, we could know about waves. But it turns out that if I gave you, and this is a very key idea here, if you never knew about these waves here, and I gave you this complicated looking wave, right, you could actually decompose this wave into these three primary waves. And that's the key idea behind why looking and analyzing physics through the lens of waves is very interesting and important. The idea here is that now if I give you a really complicated looking type of wave or signal represented as a complicated wave, I can decompose it into these basic building blocks of simpler periodic waves. So far, so good. Now, this is exactly this idea of the Fourier series, which is that I can take a very simple wave and decompose it into simpler waves. Well, that's exactly what instruments do. And that's exactly what your ears do. when it gets a sound wave. Your ears naturally will decompose that sound wave into its primary, into its primary components. And so what we're looking at here is a picture of what happens if I blow a note into a woodwind instrument. And what I want you to take away here is the longest wave that an instrument will vibrate will correspond to what we call its fundamental frequency. This will be the lowest note that this instrument will, could play. All right. If I actually cut that wave in half, right, I'm going to get another wavelength. And if I cut it in third, I'll get another wave. And it turns out that this series, this Fourier series that I just showed you here, right, is nothing more than a very common scale that you know in music, the major scale. So here we see that all the music that we know, at least in Western music, is nothing more than a representation of how waves come together, all right, and how waves can basically interact to create music. Now, this idea of using music to analyze physics was nothing new. In the 1600s, Johannes Kepler, in trying to understand the motion of planets around the sun, looked at the data and basically instead of figuring out the mathematics of Kepler's 3 laws, which was the first time that was ever done in human history, he used music as a tool of analysis. So at that time, all natural philosophers were required to know music theory. This is not the case actually today, right? But back then, a person like Kepler in his training also had to know music theory. And so he used that as a tool to write down the notes associated with all the planets. So that was an intermediate step that then led him to coming up with figuring out that the planets are going around a mathematically elliptical orbit, okay, known as Kepler's laws. So the question is, can we play the same game today? And what we're looking at here, now this is the punchline, not the punchline, but we want to now understand whether or not we can use music in a more modern sense to understand this picture here. This picture here is a pattern of the distribution of galaxies in our universe. So let me see if we can understand that. If I pick a little point here and I zoom out, right? And I continue zooming out, every dot that you see here corresponds to a galaxy like our own Milky Way galaxy. But if I zoom back out, right, you see that every galaxy forms this sort of superstructure that seems to be interconnected. And the question here is, if we go back 14 billion years in the past, this pattern did not exist. These galaxies did not exist. So the question is, how did they come about? And that's one of the questions in cosmology. And so in actually last year, not this year, but last year, the Nobel Prize was given to Jim Peebles at Princeton University for figuring out what that physics was. And it turns out that he was able to solve the problem, not through only solving the equations, the very complicated set of equations coming from Einstein's theory, but by having a physical insight first. And that physical insight was sound. But if you think of the universe as a system that's producing sound waves, then that gave him the correct intuition to then analyze the equations and find a solution. So I'm now going to explain that a little bit. Okay. So to understand that question, what we can see here is that in the early universe, roughly 14 billion years ago, the universe did not look like this, but it looked like this. So in other words, what does this mean? If I look at the night sky in every direction, what we see is that basically you see this blue and red spots. I want you to think of that. The picture that you should have in your mind is, think of the surface of the ocean. So you have, the ocean is covered by water, and then you have water waves, like ripples on top of the water. Sometimes the ripples can be high and sometimes it can be low. And these different colors correspond to a ripple being high and ripple being low. But instead of the ocean comprising of water, this ocean in the early universe, the universe is filled with energy and radiation that is wildly undulating with waves, okay, of energy. That's what this picture is. This is a picture of the universe where, in the early universe, where it was very hot and dense. Remember, the picture that the universe is expanding. That means if I go back in the past, the universe was much smaller, it was hotter and much more dense. And all of the matter that we know today were dissociated into pure radiation and energy. And this radiation and energy is undulating and dancing like waves, right? And that's what the universe was. Now, as the universe continued to expand, and it would cool, it would get colder as it expanded. And therefore, these very highly energetic waves will then basically do something else, and we expect them to become stars and galaxies. But the question we're going to ask here is, how did this early universe that's undulating and waving with energy, how did it become the stars in the galaxy? And so the insight is to understand that these waves are really sound waves. Why are they sound waves? So remember, if you're speaking right now in the room that you're in, the reason why you could be heard is because the air molecules, right, vibrate, right? And the vibrations that the air molecules undertake basically correspond to the air molecules compressing, right? And relaxing, and compressing and relaxing. And when it compresses, right, then pressure builds up. There's more pressure, there's more force, like a spring. If I compress a spring, there's more pressure. If I relax it, the pressure reduces. So basically a sound wave is nothing more than what we call a pressure wave. That's why, so does sound need air to travel through? No, because if you're underwater and you make a sound, you can still hear sound because the water molecules are undergoing the pressure wave as well. So the early universe is that situation. The energy contained in the universe, and as soon as you have vibrations of energy, those waves are nothing more than pressure waves, which are sound waves. So now I'm going to show you a really interesting picture. Now, when you look at this picture, it looks very chaotic. Why should these waves have anything to do with, when I saw this when I was a graduate student in 1990, I looked at this, it looked very chaotic. I was like, wait, this universe is not a really ugly place. But now if I analyze this through the lens of sound, through the lens of what we spoke about earlier, these pictures of waves. So remember, the key insight here is if I look at this bottom picture, this is a complicated looking wave, but I can always decompose it into similar looking waves. And if it is something that's musical, then it will present itself in some orderly pattern where I get certain types of tones or notes. So that's exactly what Jim Peebles did. He said, I'm going to take this complicated looking wave here, and I'm going to look at it, I'm going to decompose it. And that's exactly what we do with the data, actually. When we take the WMAP satellite that spent many years in outer space, taking this picture, the groups of physicists that analyze this, literally, that's exactly what they did. And if we do this, we get this picture. So what does this picture look like? Well, this lower number here corresponds to very big waves of very low tones. And as I go up and up in tone, okay? Now you notice that there's a very interesting pattern here, that at a certain point here, the height of this wave is really high. So this y-axis here corresponds to the loudness of the tone. So that there's a given tone that's the loudest. Well, let's go back to the picture of how our instrument worked. We find that the fundamental note will be the loudest note in an instrument. We call that resonance, right? And then we have these smaller notes. So what does this mean? Let's go into what this means. So just to quickly summarize, I took the picture of the early universe. I decompose it. I realize that it's a complicated looking sound wave. I decompose it into which waves are the most important ones, meaning the ones that are loudest, the ones that are more prominent. We find that there are some that are most prominent. And the question is, what does it mean? To understand that, now let's actually look at what an instrument does. So what we're looking at here is the same type of representation for an instrument. Right here, we have a flute that's playing into a microphone, and the microphone basically goes into this oscilloscope, which decomposes all of the frequencies that this flute produces, all of the waves that the flute produces when it plays a note. So if we play one note on the flute, it turns out that what this thing finds is that the flute produces many different frequencies, many different waves, actually. We hear one note, though, and that's the one that's the loudest. The one that's highest here is the note that we're going to hear, maybe in this case, as the note G in the flute. All these other frequencies that are played that we see, we don't hear it as a note. We hear it as a signature. We hear it as what makes a flute sound like a flute versus a clarinet versus a saxophone versus a piano. All could play the same note, but these instruments will produce different, these things are called timbres, right? These are the other characteristic frequencies or waves that the instrument is actually vibrating and producing that we hear as, oh, this sounds like a saxophone, or this sounds like a piano. And the reason why is that because an instrument is made up, it has a material makeup. And so what happens is that the shape of the instrument and what it's made up of, whether it's metal or wood, right, will vibrate differently based on its material makeup. So far, so good? So the lesson here is that when an instrument plays a given note, the loudest note it plays is the one that you hear. And the other frequencies, you don't hear it directly as a note, but you hear it as a signature or the timbre or the color of that instrument, what makes the instrument, and that reveals what the material makeup of the instrument and the geometry of that instrument is. But now if we look at the universe through the same lens, we see basically that the universe is actually functioning as a very simple instrument. So the vibrations that the universe is producing produces the note, the fundamental note that corresponds to the geometry of the universe. And these other frequencies here correspond to the vibration of the universe that reveals actually its material makeup. And this is why the Nobel Prize was won, because this picture, the red curve corresponds to what Jim Peebles actually calculated with the mathematics, but he couldn't have gotten to that without this intuition of sound, okay? That the universe is really functioning like a musical instrument. And this black dots here corresponds to the data that was found some 30 years later. This red curve was a theoretical prediction that was done in the 70s. And these black points here correspond to the data that was found in the 1990s, right? All the way to 2018. And so what does it show? Basically, we were able to, while it's cute and it's a beautiful, almost literal analogy between how instruments function to produce musical notes and how the universe is functioning and its vibrations to produce these tones that the universe is producing, it actually helps us understand a very fundamental question. And the question it helps us understand is that this resonance pattern, the loudest notes, gives us the information about how the first stars are formed in the universe. And these other secondary and tertiary waves give us information about the composition of the universe. So from this data, we are able to know 30 years ahead of time before that the universe was made up of dark matter and dark energy. And then later on, we had other independent measurements and looking with telescopes to agree with this data. So the same way that a vibrating instrument can reveal information about whether its material makeup, we can use the same analogy to understand the material makeup of our universe. So I'm gonna I mean, there's a lot more I can talk about. I encourage you, of course, to read my book. I go into 300 pages of glory, talking about all the different ways I've discovered music is connected to physics. This was one pathway. And I thank you for your time. And it's been a great pleasure. And if there's any questions, I'm more than happy to take any questions.
There is any comment, any question from here? If we are facing some climate change, can you use the music to predict? Well, of course, that we have seen from your lecture the relation between the structure of the universe and the music. Can we use the music to predict the changes in the structure of the universe due to this climate change? Let's say the melting of the Arctic and so.
I think that yeah, that's a very good question. Let me say that what this tool of analysis and this tool of thinking about phenomena through the lens of sound and music fits into a very beautiful field called sonification, right? Where by listening actually to data through the lens of sound can reveal structures that we can't see maybe if we present the data more visually or numerically or things like that. But looking at it through the lens of sound or hearing it through the lens of sound might be able to reveal structures that we can't see through these other means. So I think that's a really good question. I mean, to answer that question, of course, I think, it's also when we look at waves happen on certain time scales. So the question is, what are the time scales that we should look at? These, sort of like the periodicities, or if you want to say the changes, right, having to do with climate change. So I'm just throwing that back to you as a question. I think it's a very good question, though.
Thank you. Susanna, can come here, please.
Hi, Professor Stefan. Thank you for your presentation. Wonderful. I'm Susanna Sad. We are having problems with sound, so I have to come here from the audience. I just have one question for you, because you're speaking about, sorry, I'm going to take this. You're speaking about sound and music, but you're speaking about music, but actually you're speaking about sound. So where is the human activity that we need in order to classify these sounds as music? This is my question for you. As you are a musician also, and the jazz musician is wonderful one. So I have this.
How could you? Good call. Could you ask that one more time, because I had a lapse in my audio.
My question is that you've been talking about sound.
Yes.
But also about music.
Yes.
So my question about these sounds is if they are really music, because where is the human activity that helps us, or we need to define something as music?
Very good. No, you're asking the hardest question of them all, right?
Yeah.
There is a sense in which humans, we as humans, we make music, right? But I have a colleague, and you should in the future. So that's right. So there's sound. Now, let me just say two things. In the jazz world, as you know, in the avant-garde jazz world, people like even John Coltrane and Ornette Coleman, Eric Dolphy, they talk about, they refer to sound. There's an equivalence where they talk about this music as not music in the sense that we think about it as ordered, structured notes, or chords and notes and rhythm and these things, right? How they come together to make music. But they think about it as sound. They say, well, on a more higher level, all music is really sound. There's a great album that John Coltrane produced it's called Coltrane Sound, right? And so it touches on this question about what is music actually, right? And there's a whole universe, as you all know, about that. Now, what I will say that is interesting, if you can hear me, can you still hear me?
Yeah.
Yes.
Okay.
All music.
Actually,
Sorry.
so when my colleague David Rothenberg just published a paper, it's a 50-something page paper where he analyzes Mockingbird, the songs of Mockingbird, and decomposes that as a structured composition. So now what we're learning actually is that we're not the only ones, human beings, right, that's capable of actually making music, right? And so if we then say, well, where does it end? Is the universe maybe making music, right? And are we really just a manifestation of the universe's music? If we want to take my analogy very far, then that's kind of where we're getting at here.
Okay, thank you. No, my question is that, of course, all music has sound, but not all sound is music. This is the equation that we have to.
Well, yeah, that's right. I mean, but again, this is very subjective because people like John Cage, the composer John Cage, right, will disagree with that.
Yes, of course.
Right.
Thank you.
You're welcome.
Since there are no more comments, I will thank you, Stefan, for being with us. And I hope that in the near future, you can be face-to-face, not only do this.
Very much look forward to being in Portugal. It's my number one right now. It's number one on my list when I come out to Europe to visit. So I look forward to it.
Thank you very much once again.
Okay.
Now we return to our schedule. Can we put this on the track? Nuno, it's here. Yeah, it is. Then please. And the mask, it's difficult to see. No, you can keep it until. Vou deixar essa mesma. You can go ahead.
Okay, so good afternoon, everyone, and thank you for the opportunity to be here. I will be performing the presentation for the research unit IETA. So my name is Nuno Lau, and I will be talking about recent advances and projects in robotics and intelligent systems. I will start the presentation by presenting the IETA structure, and then I will talk a bit about a new associated laboratory, which is LASI, the Intelligent Systems and Associated Laboratory. Then I will talk about a selection of recent projects that I think are concerned with this year's Research Summit team and some recent advances, and I will provide the conclusion. So the IETA is structured around 3 laboratories. 2 of them are more application oriented and 1 of them is more a fundamental area. So there is a laboratory on information systems and processing, another one on biomedical informatics and technologies. And the one I will be most focused on today is on the Intelligent Robotics and Systems Laboratory. We also have a thematic track on intelligent systems for human assistance that includes researchers from all of the laboratories. In the most recent call for associated laboratories, there were some new laboratories that were created. One of them is the Intelligent Systems Associated Laboratory. And in fact, 2 research units from the University of Aveiro are members of this laboratory. They are the IETA and TIMA. And the vision of LASI is to advance technology and intelligent systems to support our society in an innovative, ethical, and sustainable path for the 21st century. And it includes 7 institutions, 13 research units, and more than 500 integrated members, being the largest associated laboratory in Portugal. It has 5 thematic lines on innovative and sustainable industries, smart cities, energy and mobility, health and well-being, infrastructures and highly connected societies, and on public administration and government. And I would say that IETA is present in most of these thematic lines. And so we hope that we can cooperate with the other research units inside the associated laboratory to foster our research and our links also to the community. I will talk about 3 different projects that I think are related to the topic of this research unit. The first one is called Intel Wheels 2.0, Intelligent Wheelchair with Flexible Multimodal Interface and Realistic Simulator. And here we are developing technologies for intelligent wheelchairs. And for us, an intelligent wheelchair is a wheelchair that is motorized and that includes autonomous or semi-autonomous mode for navigation. It also includes a multimodal interface that can be adapted to the user, because users of intelligent wheelchairs will have very different capabilities, and we should offer an interface that allows them to comfortably command the wheelchair. And it also be enabled with capabilities of communication with other intelligent wheelchairs or with automatic doors or with elevators and things like that. It will develop a framework or a kit that can be added to any intelligent wheelchair, any motorized wheelchair that is commercially available, and that will enable it to do the tasks that I mentioned before. It will also develop a realistic intelligent wheelchair simulator, the multimodal interface I talked, and we want to have several demonstrators of intelligent wheelchairs. The partners include 3 companies and also the University of Porto. And we can see here some preliminary results in which the wheelchair is mapping the environment. So it is traveling through the environment to provide a map, and then it is also navigating autonomously. So we can say the initial position and the goal position, and it will plan its paths through the environment, and then it will travel autonomously. So now nobody is driving the wheelchair, it is driving autonomously, and it will go from the target point to the goal point. Another project that is concerned with these times is the Germi-RAD, on automated germicidal irradial system. And this is the Germi-RAD project aims to develop an automated disinfection solution for public spaces. The system is composed of a mobile robot platform, a disinfection subsystem, and also that includes ultraviolet light and also chemical disinfection. The main innovation of this system is that the ultraviolet light that is going to be used is not harmful to people. And so it is very challenging both from the robotic point of view and from the disinfection point of view, because while navigating to the past, we must assure that disinfection is comprehensive, but we must also take into account mobile objects like humans that will be present in the environment. And the partners include also a company and the University of Porto. The last project that I will mention is AgroSafe Box, on intelligent alert system for agro vehicles rollover and driver safety. And here the purpose is to build a box that will be attached to an agro vehicle. And by monitoring the dynamics of the vehicle and also the health condition of the driver, we want to prevent accidents. And then if an accident occurs, we also want to call for help in a more adequate way. And the model that is concerned with the Aveiro University is mostly the driver health status monitoring. And we will do that via pre-driving protocol, by monitoring the vital signs, and also using computer vision to check if the driver is stressed or is sleepy. And the partners include 2 companies and also the Polytechnic Institute of Viseu. I will follow on with some recent advances that we had in our laboratory. So we have been working with reinforcement learning for a few years and with deep reinforcement learning in more recent times. And one of the test beds that we used is related with RoboCup competitions, and mainly robotic soccer, or in this case, simulated robotic soccer, in which you have 11 against 11 humanoid robots that will play soccer against each other. And what we want is to be as fast as possible and as stable as possible when we are walking or running. And the classical approach is to develop a walk engine that is based on the 0 moment points, and then optimize the model parameters in order to do it, and all teams do it, and we have been doing that for several years. But more recently, we tried to use deep reinforcement learning using a recent algorithm called PPO. And this algorithm, this approach includes a feedback cycle walk engine that, based on the current situations, it will act differently. And we start the learning phase by using ground truth data that comes directly from the simulator that cannot be used by the agent, because the agent only has access to noisy data. And then, in order to deploy to the agent, we had to estimate some of the features that we were using based on ground truth in order to make it possible to work. So I don't have time to explain all the technical details, but we start with the joints of every angle of the humanoid robot. We estimate those measures that were available in ground truth and that are not available anymore when we are deploying it to the agent. And then in the end, we have an estimation of how good the action is, and also target point angles that then should make the robot be able to run as fast as possible. What I have here is a comparison between, oops. Okay. A comparison between our approach and the current world champion and vice world champion. These data are from 2019, but in 2021, they are mostly the same. And you can see that although every team is using machine learning and every team is using optimization, we are actually twice as fast as they can be when we are chasing for the ball, which is a result that is quite unexpected, but quite remarkable, I think. Another problem that we have been tackling is on using multi-agent systems, where you have several agents that want to achieve a complex task. And of course, they should coordinate themselves in order to, for example, split the roles among themselves to manage the task. And it is also important that they can communicate between each other in order to coordinate. And the problem is that most of the times the communication is encoded. And so we wanted to use deep reinforcement learning not only to learn how to coordinate between themselves, but also how to communicate between themselves. So we do not want to encode either coordination or communication. And for that, we want the communication to be learned tabula rasa, and we have used an actor-critic reinforcement learning architecture. So in reinforcement learning, the agent decides the next action based on state, and then the environment provides the next state and also a reinforcement or a punishment value that is then used by the agent in order to learn which action it should take next. When you use an actor-critic reinforcement learning inside the agent, you will have a model that provides the value of each action, that is the critic, and another model that provides the actor, that is the actor that will provide the action. And we have taken that support, and we added a new model that provides the communication. So each of these models, the critic, the actor, and communication, in fact, will be deep reinforcement learning networks, neural networks, and that will then be deployed to several workers that will act asynchronously in different environments and will update the global networks. The networks are connected in this way, so the critic may have access to ground truth data, for example, in order to enhance coordination, and then the actor and the communication network have access. The actor has access to the latest observation and latest message, and the communication network provides the next message. And by doing this, we could, for example, you have here a system in which the black circles will search for the red circle and will try to meet there. And when they are not coordinated, you can see that the pattern is quite chaotic. But when we use our algorithm, which will happen in a few moments, you can see that the exploration is much better. So now they explore the space in a much better way. When one of them finds the spot, they immediately get there. So as a conclusion, I would like to say that IETA and TEMA are members of a new associated laboratory. We have several projects that foster health, innovation, and sustainability, and we are using deep reinforcement learning for both single agent and multi-agent systems. Thank you.
I hope that these negotiations this morning were good with the FCT about Lassie. And well, I think the first player it was Cristiano Ronaldo against Chandler, but the other one it's enjoy the game. Thank you very much.
Thank you.
The next one is CTFF. Yes, it is. Shana Sa.
Ora, então, muito boa tarde. O meu nome é Xana Sá Pinto e I'm here on behalf of the BiblioLab team to present you the BiblioLab project, which aims to understand how can we co-construct transdisciplinary solutions. And I'm also here on behalf of CDTFF, and BiblioLab project is just one among several amazing projects that are currently taking place at this research center that address sustainable goals such as learning equity or poverty, or even understanding each other. And that also addresses problems such as species conservation or air quality. So I strongly encourage you to take a look at our website or to our YouTube channels and learn more about other projects. So when we think about these problems that we face today, they are very diverse. They range from climate change to fires to resources problems, pandemics, but there's something that they all have in common, and that they are pretty complex. They are complex in the sense that they have generally multiple causes, and these causes are interconnected. Moreover, there are several agents, several different people that are related with these problems, and sometimes they have very different perspectives, very different values, and sometimes even conflicting interests regarding these problems. And so solving these problems require, there's no such thing as a simple solution. So if we focus on one of these projects, so let's think about, for example, the fish stock decline, you can immediately think about several agents that are related with this problem. So such as researchers, such as biologists, or oceanographers, or the policymakers, or the fishermen, or even the fish consumers like me and probably you. And we all have a very different way of seeing these problems. For example, for a biologist, it's a conservation problem, or it's an ecosystems problem. But a politician see it as a management problem. And for fishermen, it's a very strong problem that is related with their daily income and with their jobs. For me, as a consumer, it's a problem of resource availability. How many times I'll have sardines in the next San Juan. So the way we see the different problems and the experiences that we have with them and the knowledge that we carry each one of us can have a very different solution. The problem here is that if we don't take into account other people's understandings, perspectives, values, and motivations, these solutions, when implemented in the field, they will most probably fail. And so addressing these complex problems requires solutions that are built that are co-constructed with the different partners that paid attention to their different motivations, their different interests. They are built informed in different types of knowledge, different scientific fields, but also the procedural knowledge that the practitioners in the field have about the problem. And so it requires problem-solving skills. It requires the ability to work with different types of knowledge. And it requires also creative thinking, because we need to be creative to create solutions for these problems. And all this turns out to be an education problem, because education should empower people with the skills and knowledge needed to address sustainable development goals. And on the other hand, we are talking about effective partnerships. How can we foster sustainable and effective partnerships that can address the sustainable development goals? And while we are working around these two very important goals, we'll be also working on all the others, because all the others depend on these very important transversal goals. So our idea to address this problem is through transdisciplinary education. So transdisciplinary education is an approach where students learn the discipline contents, but in a context that allows them to apply and link the knowledge from very different disciplinary fields in order to solve a problem or to come up with a product that they are asked them and that they are seen as relevant for the context. And we know from research that transdisciplinary education helps students to think across disciplines. We also know that when we have science, maths, and arts all together in these transdisciplinary education approaches, the students' motivation increases, and there's space for the development of collaborative skills and also creativity. However, research also shows that these approaches are still very scarcely used. And part of this is due to the fact that the teachers do not feel confident to plan and to implement and evaluate this kind of educational approaches. Furthermore, the few resources that are available, in most of them, artistic education is typically less developed. And so it does not allow the students to develop artistic skills as much as the other disciplinary fields. And finally, in many cases, the learning outcomes are most often assumed than evaluated. And this highlights the need for additional research about this topic. So let's think about transdisciplinary education, what we need to make this more common in schools. And when we start to think, we realize that the scarcity of transdisciplinary education is a complex problem per se. So what does that mean? It means that there are several people that are related with this problem. So here in the academia, we have knowledge about how to foster this kind of education, but the teachers or the science museum staff are the ones that can implement these strategies in the field and that deal with it. But they are not alone. They are affected, the way they are practiced are affected by multiple factors, by the school board members, by the national policies, but also the kids they have in front of them and their parents, and also the teacher trainers that can help them doing this more often, or even other entities that can occur in their locality and can support them. So in order to overcome this problem, we have several questions that need to be addressed. So how can we develop these effective transdisciplinary education resources that articulate science, maths, and literature as an example of art? how can we empower the educational stakeholders to plan, implement, and evaluate these kind of resources? And how can we foster these sustainable partnerships that can support the educators in doing this? And finally, what are the impacts in students' learning? And in order to address these questions, we come up with BiblioLab, which aims to promote more transdisciplinary education in schools. And in order to do that, we will use a transdisciplinary research approach. According to the research, this kind of approach is very effective in co-constructing sustainable solutions that are effective on the field, to produce scientific knowledge, but also to empower the different stakeholders with the skills that they need in order to overcome the problems. Typically, these transdisciplinary research approaches have 4 phases. The first one is building the communities. The second one is within these communities and with these communities to rephrase the problem, so it takes into account every people's perspectives and way of seeing the problem, and to define research goals and questions that make sense to all the stakeholders. Then together we will co-construct not only the solutions, but also the methodology that we will use to do research, and where everybody will have their different role. And finally, we will go to research results dissemination, which again will be done by all the different stakeholders. So we are in the BiblioLab in this phase 1. We are starting to build the communities. And in order to do this, we ask these questions. So who has the scientific knowledge about this problem? And who has the experience in the field to handling this problem? Who is affected by them? And who has the power to tackle it? So answering these questions, we come up with our partners. So at the moment, we have 4 different learning communities. And in each of these communities, we have very diverse members. Some of these members will contribute with the scientific knowledge, and these are coming mostly from the University of Aveiro, namely our center, but also other centers where we will find a necessity to go and find people and experts, but also from the University of Trás-os-Montes e Alto Douro. Some of our members will contribute with the normative knowledge, the knowledge about the goals that the society is expect us to achieve, and the values that should guide us. And these are the mayors in the town, but also the school board members. And finally, we have members who will contribute with the procedural knowledge that they gain from their practice in the context. And these are, of course, the teachers, the people in the science museums, in the libraries, in other local museums, and also in a science education company. And so we are here at the moment, so I cannot tell you much more about the project. We hope during the next school year to start defining the problem, research the questions and goals, and also to co-construct the knowledge and solutions. And in 2020, until 2023, we'll be doing this, but also disseminating our results. So if you want to know more about BiblioLab, I would just encourage you to follow us on our social media or on the website. And I would like to thank you all for your attention. Thank you, and I'll leave you with our team. Thank you.
For this interesting lecture and to bring us the transdisciplinary, that is what we are expecting and trying to achieve. Thank you very much. Now, Alex from LLC, please.
Okay. Thank you very much. Claro. Boa tarde a todos. Good afternoon. We heard in the last talk about transdisciplinary ways of teaching, and I'm going to speak about transversal research in languages, literatures, and cultures. My presentation is divided in 3 parts. In the beginning, I will introduce the Center for Languages, Literatures, and Cultures as a transdisciplinary research center and briefly explain how it's organized. In the second part, I will refer to the research center's events in times of pandemic from March 2020 to present time. And to conclude, I will try to anticipate some possible trends of our research center in the near future. The organization of CLLC reflects the variety of scientific areas represented in the Department of Languages and Cultures. This diversity has not always been easy to manage, but it has been consolidated since 2013 through a structure organized in 3 major groups covering the areas of literature, culture, and language sciences. This organization has proved fruitful in terms of scientific production and interdisciplinary intersections. But we must not forget that these 3 major groups are in turn subdivided into 3 or 4 projects each. And this gives rise to a very wide web of themes in a total of 10 projects. So the major challenge of CLLC has been to establish a framework which is broad enough to accommodate research of its members, but at the same time limited enough to allow interaction between researchers. CLLC's research program also represents a scientific basis for our graduate and undergraduate and postgraduate training, namely for the doctoral programs in literary studies, cultural studies, translation and terminology, and more recently, language sciences. The number of junior research members has been increasing as a result of these doctoral programs. And here I can say that at least in 2 of these programs, the pandemic has contributed with students from all over the world, from different countries and continents, which otherwise would probably not have chosen our university. But how can a rather diversified research center maintain its unity? First of all, researchers collaborate in more than 1 project. And second, collective activities reinforce links between projects and groups. Transversal conferences are a good way to put this in practice and bring together such diverse areas as literature and language sciences. Transversal conferences started in 2017 with International Conference Moving Texts, which explicitly sought to trigger the discussion about interlinguistic and intercultural dialogues from different standing points, linguistic, cultural, or literary, and to encourage the intertwining of disciplines. And I would say that this goal was achieved. Then in many cases, it was difficult to separate the talks, to place them in a specific topic because they were at the same time dealing with literature and culture or with literature and translation, for instance. In 2019, we had the emergence of concern about fake news, manipulation of information, censorship, and taboo words set the theme for a new transversal conference. And treacherous words can be approached from different perspectives and in different domains: literary, cultural, language, and translation studies. A new transversal conference is now being prepared for 2022, and the topic is Changing Worlds. and we hope to be able to gather again research from different fields, literature, cultures, and language sciences, and perhaps a more distanced reflection on the influence of pandemics on languages and cultures. The second part of my presentation deals with research in pandemics, and I will draw a line with this conference, Words in Revolution, that took place in the beginning of March 2020. It was the last in-person event at the Department of Languages and Cultures and focused on the recent evolutions in the field of translation driven by technological developments. At the same time, when confinement had already been announced, the focus was on machine translation and particularly on its newest version of neural machine translation. This evolution affects not only the translation process in itself, but has also repercussions in translator competences, training, assessment, etc., which should be discussed in the academic and in the professional fields. Another aspect of this, After this event, the conferences and seminars that had been scheduled for 2020 were cancelled or postponed. Why? The reasons are easy to understand. No one knew for sure what was going to happen next. And the first reaction was to wait for the moment when face-to-face contact could take place again. Online participation in events was not completely new, but it was exceptional, not the rule. Nevertheless, life went on and so did research online. Gradually, conferences and workshops returned in form of online seminars. Some of these events are sequential, bearing upon past events of the same nature. For instance, this conference cycle in editorial studies, or the conferences in linguistic variation with a tradition in our department. Others were favored by the new online conditions and were able to take advantage of this. By observing the posters of these conferences that were organized by the CLLC, we noticed a strong international participation. For instance, in this conference of cartographies of cultural studies. Another aspect of this option, another aspect of pandemics was perhaps the option of spreading seminars over weeks. This seems to be a strategy to cope with online fatigue. For instance, the conference Mix and Match, organized by the project Between Genres, has 3 sessions in different months. And this last slide shows the poster of the most recent event online, organized by the project Languages and Learning. Other conferences will take place in autumn and winter, but it's not yet sure of if they will be online or face-to-face. I believe there is a desire to promote conferences where one can question the speaker and closely observe the reactions of the audience. The direct exchange of impressions and the appreciation of the audience is an essential part of academic forums, as we know. The possibility of continuing the discussion in the corridor between one talk and another is sometimes even more productive than what happens in each room. Being able to observe the reactions of the audience through facial expressions and gestures, the buzz generated by comments with the person sitting next to you, is something that screens inevitably lose. I cannot anticipate the future, but I believe that our research center will resume to organization of research events with the presence and contribution of researchers in face-to-face events. Nevertheless, in many cases, the experience of pandemic will mark the nature of future research sharing events by making them possibly more flexible and hybrid, such as this one. This will allow speakers from less evident countries to participate via the internet in a hybrid conference. This is a strong incentive to include researchers who might not be the first choices in selecting keynote speakers because they are from different continents because of the distance or for economic reasons. And this is a positive gain from this negative experience of COVID. To conclude, I would like to point out some possible trends for the near future. The reinforcement of links and partnerships with other institutions, possibly to consolidate and extend more of the context that already exists, and investment in dissemination infrastructures, online publications, and websites to disseminate the research of our various projects. And thank you for your attention.
On this lecture, the advantage and the disadvantage of the COVID. We hope that the next one can be face to face.
Yes,
thank you.
we hope so. Thank you.
Take off.
Okay. Thank you. Oh. Thank you. Good afternoon, everybody, colleagues. So this presentation is about what we do in Institute Telecommunications. And according to the topic of this research summit, which was Art and Innovation in Times of Trouble, I decided to call it the Bypassing Social Distancing Through Communication Technologies. What is that in IT do we do for that? Well, being IT, the Institute of Telecommunications or the Institute of Telecommunications, what do you see? What we have right now, the way we are communicating is what we do. So the outline of my presentation is, first, I will start with an introduction, then I will say some words about secure communications using quantum cryptography. Then I will talk about Internet of Things, namely vehicular communications, and then I will say some words also on how is it that this stuff is done, by showing some examples of research on RF circuitry for RF wireless communications. So what would be social distancing without telecommunications? Commerce, stop. Work, stop. Formal education, no way. Healthcare, too much reduced. Human relations, kept only at the family. Information and immediate distribution of rules throughout the country, impossible. Telecommunications provide e-commerce through the internet, telework and teleschool via email, audio and video calls. It also presented a big help via remote healthcare. For example, in my own case, I was amazed how I could be, how I could talk with my doctor, and she made a diagnostic almost at the time with a phone call and some photographs. Human relations through social networks, email, audio, and also video calls. Immediate distribution of information by the hour and everywhere via the internet, television, radio, etc. One thing that I would like to call your attention to is, imagine if we hadn't no telecommunications, how would we be able to say, this afternoon or this evening, the restaurants will close at 10:30, for example. How could we spread this information by the hour? In the near future, the fifth generation of telecommunication networks, the so-called 5G, will provide totally integrated transmission of data, voice and video, no difference between telecom devices and computers or microcontrollers of industry. Telecommunication networks and computer networks will be the same, which will enable or foster even further cloud computing. Internet of computers will turn into the Internet of Things, that is the Internet of everything, smart homes, digitalization of industry, remote surgeries, and artificial intelligence added diagnostic, autonomous vehicles, safer, more efficient, and thus environmental friendly mobility, and so on and so forth. It's almost limited by our imagination. In IT, the research fields that we cover are wireless technologies. You see, yes, wireless technologies, optics and photonics, information and data sciences, networks and services, and then basic sciences and enabling technologies to support all the other applicational fields. Now let's see what we do in terms of secure communications using quantum cryptography. Using, for example, discrete variable communication systems, what we are doing is encoding information in the polarization of single photons that we transmit and we detect in a fiber optical system. We can do it also with or via continuous variable communication systems using nowadays quasi-single photon pulses. But we also can provide the generation of true random numbers. Actually, I say here true random numbers because they are based on the vacuum quantum noise. And so as far as we know, they are true random, whereas all the other random numbers that we now generate, for example, in casinos and so on, are what we call pseudo random numbers because they are actually repeated and can be somehow manipulated. Applications of this are secure communications with quantum key distribution, the quantum secure multi-party computational services, which are a very interesting idea in which, for example, imagine that a group of us wants to compute all the money that we have. We can compute all the money that we have, but we don't need to provide our money to the others. We only know the result and we know only our money, but we do not provide that information to others. Also, what I said about random, true random number generation and prime numbers also. Projects in this optical quantum communications and technologies group at IT Aveiro are the QRunner, internal project funded by IT, the quantum mining funded by FCT, quantum dot funded by the P2020 program, also the Q-Prime and the QGAS or QS funded by FCT, and the Q-Genome funded by the Austrian Institute of Technology. Now, let us turn our attention to a different field, which is Internet of Things, and in particular, for this case, or for this example, vehicular communications. That's what we do in the embedded systems group at IT Aveiro, and what we do there is vehicle to everything communication. Actually, this vehicle to everything can be seen as vehicle to pedestrian communications, vehicle to other vehicles communications, vehicles to the wireless network of mobile communications, for example, and also vehicle to the infrastructure, namely the traffic lights, for example. Examples of projects that we do in this embedded systems group are the 5G MOBIX, which is a European H2020 funded project, then the STEROID, the PASMO, and the TRUST, which are all P2020 projects. And I show you here how these projects distribute in our country, because these are real implementations in the field of vehicular communications. Finally, how do we do this stuff of wireless communications? The example I'm going to provide here is to mitigate the transmitter performance degradation under load modulation. What is that? Well, imagine, for example, what we call the end effect, which is I pick up my phone, I'm radiating a wave. This wave, in principle, does not reflect anywhere, and so the amplifier is seeing a certain impedance, a certain load. But if I put the hand like this, then the wave will be reflected in the end, and so the amplifier will see a completely different load, degrading its performance. Something similar happens whenever I have multiple antennas, and the antennas can communicate to each other, so that one antenna radiates, comes back to the other antenna, and in this other antenna, the amplifier sees a different load. This is a very important thing nowadays because of its application in what we call MIMO systems, multi-input, multi-output systems in wireless communications. And so we have been doing research on that, funded by company. The way we mitigate this problem was to take a sample of the output of the amplifier. With that sample of the transmitted wave and the reflected wave, we measured the impedance, and then we controlled the input of the amplifier, the signal that is exciting the amplifier, as well as the power supply, to overcome that problem that I told you. This is a photograph of the measurement test that we have there in our laboratory. And this is an example. Of course, I will not enter into any details, but simply showing you that without compensation, you see a spread of these curves, whereas with compensation, you see a much more confined set of curves, which indicate that, in fact, the system is compensated. Examples of projects on this field are the OMIMO, funded by FCT, the Joint Lab, funded by Huawei Technologies, and the GANLIN, which is funded by Amplion, former the Philips Semiconductor in Holland. And that concludes my presentation. I thank you very much for your attention.
Thank you very much for your introduction. And in the first part, highlighting the problem that we face if we don't have the telecommunication. Perhaps in a horse and a man running along the city, it will be fine. Well, thank you very much.
It's very important, I believe, the control of the society, spreading the information and controlling the society so that we can respond effectively. Telecommunications are very important for that. Thank you for the opportunity.
Well, we must finish this first session, thanking all the speakers, and I think we must do an applause for the 5 of them. Since we are out of time, we don't have break. We go immediately for the second section, because at the end we have the minister and we want to be more or less on time. And I move on now to Cristiana Silva for SIDMA.
So thank you very much for the opportunity of being here. I'm representing SIDMA, and I am member of the system of control. I am member of the group of systems and control, and I will speak only about a little part of the research that is being done in SIDMA, and I will focus on mathematical modeling and optimal control of epidemics. So both mathematical modeling and optimal control are parts of a branch of research that were born in times of trouble, like this, the topic of this research summit, mathematical modeling. So we can say that one of the first mathematical models for in epidemics was proposed by Daniel Bernoulli when he wanted to calculate how much our lifetime will increase if it will be created a vaccine for smallpox. And it could not be more actual, because now every day we speak about vaccine for COVID. And optimal control also was born after the Second World War to solve problems of engineering. So in our research unit, for many years that members of our research unit are working on mathematical modeling for infectious disease. And our aim is to try to describe the evolution of an epidemic related to, for example, we worked on Zika, on Ebola, tuberculosis, HIV, and we wanted to describe the dynamics of for example, nowadays we could describe the active infected individuals with COVID, and we did this for many other outbreaks and diseases. And these mathematical models, what we can do with them is we can investigate how can we change them, or what are the causes that are forcing the curves to increase or decrease, how can we control them. And we can see that this could not, this is very, what was studied 200 years ago, nowadays has been tremendously also used, and we can do a comparison. For example, the image from in the beginning of 1926 and now in March 2020, we could never imagine that we have a very similar situation. So what we want to do is to apply optimal control theory that, as I said, is very used in engineer, and we can say that is also a branch of engineer. And for example, we can use optimal control theory to control a spacecraft when we want to, for example, or we want to put a satellite in orbit. This is an optimal control problem. But also we can try to control an epidemic curve. So we have the curve of active infected individuals, and we want to go to that is as a starting point, and we want to lead this curve to an end point where there will be no infected individuals, for example. And this is an optimal control problem. And we have done this also applied to tuberculosis, HIV co-infection with tuberculosis, and many. And for example, this can also be done in cellular models. For example, if you want to try to find the optimal chemotherapy for cancer, or innovation therapies for many other diseases. So this can be not only a population level, but also a cell level for many diseases. So this we have experience in this field, and when we were in the April 20 of last year, there was this call, and we applied, and because we had we were working was really where we could apply our knowledge, and we got funding for a small project of 3 months, and this project was to apply optimal control and mathematical modeling to COVID-19 pandemic. The promoter was the University of Aveiro, coordinated by me, and we had the partners, the Unidade de Saúde Pública da ACES Pinhal Litoral, and the Escola Superior de Saúde do Politécnico de Leiria, Escola Superior de Enfermagem do Porto, University of Vigo, University of Santiago Compostela. So there were doctors, there were people from mathematics, from physics, and we tried to apply this optimal control and mathematical modeling, and also complex network to COVID-19. So some selected publications that we can mention. We tried to see how we could apply a control of the deconfinement for Portugal, because this project was from June to September 2020, and so we were in May. We were the state of emergency ended, and what the main problem is how to deconfine, and so we tried to solve this problem using optimal control and also mathematical modeling. And another thing that we can mention is this problem about this complex network model. Where we also studied when we speak about when there is no movement between regions, these cerca sanitária, these lockdowns, and so applied to COVID-19. So one of the problems that we are able, or we tried to solve, was how to deconfine, or let's say how to let people out of their homes using the protection measures and go to work and teleworking, but ensuring that the maximum number of infected individuals is also below a maximum number that should be defined by the health authorities, and also ensuring that the number of beds in intensive cares and in nursing is also under a certain maximum number. And the solution is indeed the solution of the optimal control problem that we have seen also in a talk previously, when it was the on and off. It's the same solution that we have here. We have on and off, but applied to confinement. So the solution was to set free, end the confinement. But then, the more we let the society to be free, the more time then a lockdown will be imposed. In this work, we fit the fit of the model to 6 regions in Portugal. So 6 because we include the Pinhal Litoral. We have the classical 5-1 and the Pinhal Litoral. And then we tried to analyze which would be the optimal topology. It means that which should be here the arrows that should be erased. It means in between each region we should stop or no the connections in order to minimize the number of active infected individuals in the whole country. And we did this. What we conclude was that it's not when we consider the empty topology. It means it's not when we consider that no one's go out or for its region that is the optimal. So this black line, it's the empty topology. So when we say no one goes out from his region, it's not the optimal, but of course it's very far away from the worst, this one in red. But there are other solutions that are not optimal, but that are other solutions that we can consider when we can let people move between some of the regions, but other regions must be should be confined and with no movement. So this to end and to say how we contribute to the science in times of trouble, we think that these themes are very actual, because we think that when our government choose to say controlar a pandemia, it's in fact what we use in our articles and our papers. And we have here this news from University of Aveiro when our paper was published, and even our president speaks about the same title. So we want to find the balance between setting free our lives and the increase for the good of the economy, but at the same time to control the number of active infected individuals. And so it's all.
For showing us how fruitful was the smaller project that we have in COVID. Thank you very much. Next one, Stefan. I see the end.
Good afternoon. So pandemics, as we already heard, are with us for a long time, and there are historical reports that tell us that maybe 3,000 years before Christ there was already pandemias, but more recently we know for this black plague that crossed most of the world, or at least part of Europe, as you can see here in the middle of 14th century, where lots of people died in that time. But especially you can see in this map how this pandemic, the flow of this pandemic through the different regions, and the time it takes from going, for instance, from Mecca in 1349 to, for instance, to Portugal or to the North Europe. It takes 5 years or 6 years to spread around Europe. Later we have last century we have the Spanish flu, very known for many people, where the estimation is that 50 million people died in this with this pandemic. Since then, many others happened, even recently, in, let's say, in the last 20 years. You remember SARS-CoV-1, Ebola, and lots of them already mentioned here today. But so these we could learn, in fact, from these examples of previous pandemias. And when I say learning, means that eventually, when we face a new pandemic, we can predict what will happen, or somehow predict the future. Unfortunately, we are passing now very severe pandemic, and in fact, the previous knowledge apparently doesn't help much in prevent and in making predictions with this present pandemic. So the goal of the studies like the one we saw before is to somehow help the institutions like governments or health institutes to somehow predict and prevent, as I said, these pandemias. But if I ask you what distinguished these three last cases I show you in 5 centuries, more or less, time gap. So if you pay attention to the pictures, in fact, the thing that distinguishes these three situations is basically the density of population and mobility. And this is the problem we face now, for instance, with this pandemic, is mobility. Because nowadays, contrary to the previous pandemics where it takes 6 years or more to spread all Europe, now it can take 1 day. So if I ask you, if our goal is somehow to predict, so suppose we are now in the middle of March 2020, and we have this pattern there with that is the evolution, so very few cases in Portugal. And if I ask you to predict the number of cases, for instance, 1 month later, can you do make an estimation? Well, in fact, not. You see, when we go to this, something happened here. But for instance, if I ask about 4th of November, you see there is the huge peak on the day 4th of November with more than 7,000 cases. And you cannot predict from the first line I have there in green, you cannot estimate that some months later, this will be the situation. But if I ask again, and in January 28th, what will happen? So you see again another peak with a suddenly increase on this number of infected people. In fact, you know now the picture. So this is data. This is the present data, the evolution, present evolution, and I put there a butterfly because there is something very known in the forecast, weather forecast, that is the butterfly effect, where people say that if a butterfly clamps the wings in Brazil, there be a tornado somewhere in the world. And in fact, similar effect happened on 24th of December or around 24th of December, as you well know, and we have this sudden peak in this distribution of events in the beginning of the year. So predicting the future, in fact, is not easy. So if you know this curve, this black curve that has, so imagine that the dot is the present day and we know the past, but if we want to predict the future, any of these 3 curves or any other in the middle, in principle, are possible. So it's very difficult to predict, in fact, the spreading of an epidemic. And as I say here, in fact, prediction of an epidemic is an exact science. So there is one case that we should also learn before. So here you cannot see the map, but it's supposed to have a map, a world map somewhere here. So this is a very known case. So there was a pandemic over the principle of some pandemic in Guangdong, so in south of China. And there was a doctor that is in the hospital playing with these people, these patients. And he moved to Hong Kong and he checked in a hotel called, become famous, Metropolitan Hotel. And during this night, he interacted, of course, with different people. And the day after, this physician went to the hospital and he died a few days later. And the problem is he also passed the disease to other people. And these people traveled to Vietnam, Singapore, China, Toronto, etc. And so in the next day, the disease that they took in Hong Kong in 1 day was, as you can see, in 5 continents around the world. This is the big problem. And this is, they could identify the people that intervene in this spreading of the disease. And in fact, there are 5, the doctor is this guy in purple, and the other 4 main guys are responsible for spreading disease, Singapore, Canada, Toronto, etc., Vietnam, etc. So these are what we call super spreaders. And so the idea is to understand the effect of these people. Because in most of the models that we use, and we already saw here results today, it is assumed that everybody interacts with everybody, and this is not real. So no, we don't interact with everybody like in these models or kind of midfield models. So different people have different number of interactions, as we can see here. So there is a certain heterogeneity in the number of connections that we have, in the average number of people we interact per day. And these have consequences, of course. So just after we done this work, I will show you in middle of January, there appeared this paper precisely in February in Nature, where they say the super spreading problem. And they talk about this 80-20 problem of that we already listened this morning here, that 20% of the cases are responsible for 80% of the consequences. So this is the idea of the super spreaders. Very few are responsible for a big part of the effect. Okay, like we, as a teacher, 20% of what we teach can have consequence in 80% of the things that students should know. So another problem we face when we try to simulate these things is data. So data, in fact, is very scarce, sometimes imprecise. And for instance, I took this data yesterday or 2 days ago from this Institute of Health Metrics, and you see the lower curve is the report data about the infected cases in Portugal, around the deaths, the number of deaths, because number of deaths in principle is more precise than number of infected people. The official report says around 18,000 deaths, and they estimate 43,000. So you see, more than twice. So there is a big imprecision in the data, because they count only these cases that die in the hospital, etc., and not those cases that, as a consequence of COVID, they die later, etc., etc. And this is possible to estimate because people know if there was no COVID, what is more or less the trend of the evolution in number of deaths. And we see that nowadays there are many more deaths than those that are attributed to COVID. So we proposed a model where basically we try to understand or to give some advice for the process of vaccination. You know, the protocol of vaccination that was recommended by the World Health Organization was basically start by the oldest, 8 years old, etc., and go lower and lower, etc. And we try to show, and these are the model equations, so it's not important here, but we try to show that given different people or in sectors by aging, they have different number of interactions, as you can see in the figure I will show you later. But this is just to show you, for instance, everybody talks about nowadays about R0, RT, etc., is below 1, above 1, but I believe that most of people don't know nothing about this number, how it is calculated, how imprecise it is, etc., etc. So in fact, it's very difficult to measure this quantity. And if I ask a specialist, what is the value of R0 for COVID? He says between 2 and 4.9, or between 2 and 5. But this means there are very strong, very different consequences if it is 2 or if it is 5. But so nobody knows the real value of this R0. And this is the matrix I mentioned. So you have here classes by age. So for instance, 30 to 39, how they interact with the other groups by age. And you see that, for instance, people in this green square is the oldest people. And you see they have very few interactions. You can see they interact a bit with people with 30, 39, maybe they are the sons of these old people. They interact a bit more with 10, 19, maybe the son of the son, etc., etc. So you can more or less anticipate these metrics of interactions. But you see there are lots of activity here in the center. That's why we choose one of these groups, let's say 30 to 39. What are the consequences if we start to vaccinate not only these people with more than 80 years old or 17 years old, but also vaccinate 20%, say, of this group of people in the middle, that given the activity they have, in principle, they have more connections, and the metrics of connections tell us that. So in fact, If we do this, and then we assume that the vaccine can have different efficacies, 70%, 75%, or 70%, and 95%, and you see different curves, and the different curves, the different regions, there is a lower bound and an upper bound that depends on the parameter that we introduced, that is this, if these 20% of people inside of this group aged 30, 39 have 3 times more interactions than the average in this group, or 10 times more than the average. And this is the lower end. But you see, with our procedure, is the red part, you see that it lowers a lot. So in fact, there is vaccination plan 1, that is only vaccinate old people, and there is vaccination plan 2, that is vaccinating old people, and also the group of 30, 39. And if you do this, you see that it lowers down this, the number of deaths. So this is the estimation of the number of deaths, you see, and we got this curve, so you can see here. So our curve is the red curve, so it's around 21,000 people we estimate to die. In fact, we are in 18,000, but I think our curve is this curve in dots. So you see, the real curve is the curve in dots, so how it compares with our estimation. So our estimation is a bit higher, but I think it was in part influenced by the data we use, because we start to do the simulations in this black row, so somewhere in beginning of January, and precisely there was this peak. And this peak influenced certainly a lot our data, and that's why we have an overestimation in number of deaths. But as I also show you, the number of deaths is also very imprecise thing. So this is the team that has been involved in this year. So we are working on it for a long time with different proposals. And as Niels Bohr, a Nobel Prize in Physics 1922 said, prediction is very difficult, especially about the future. Thank you very much.
I hope that we need to give this model to our epidemiologists that are in TV all the time, trying to convince them. Thank you very much. Next one, it will be Silvia Rocha, AQV.
So good afternoon for all of you. The topic of my talk are related with a kit that we created, and I will explain a little bit about this, what the idea and what is this kit and the possible applications. So as you know, COVID-19 appeared as a storm in our life, and the academic communities around the world intended to think about solutions to reduce or to mitigate the impacts of this pandemic condition. And each one of the different research groups think in solution based on their one expertise. In our case, as we are a lab specialized in the chemistry of natural products and aroma chemistry, we look for this olfactory dysfunction related with smell, the loss of smell or other types of dysfunctions. And actually, about 60% of individuals can recover after 2 weeks, but other didn't recover. And after several months, continue with several dysfunctions. And these dysfunctions has a lot of problems related with the quality of life, namely may represent some security problems. And for example, the American Medical Association reported that the training twice a day with a mixture of odorant molecules may be one of the solutions for the treatment of these persistent olfactory dysfunctions related with COVID-19. And actually, there are some information related with the receptors in our nasal cavity that has several receptors for these odorant molecules. And the interaction between the receptors and the several and specific odorant molecules may be very, very important in the stimulation and the recovery of the smell. So this is the starting point of these projects. And we think, so where we can find some odorants, some molecules responsible for the odors. So we can look for the nature, and we can find several solutions, but we establish a set of requirements. So we want a plant-based solution. We also look for some wastes or some byproducts for the industries. And we look also for the combination of other requirements, for example, the stability, the operational stability of the materials, the storage stability, the chemical composition, because the idea is not to use any other extra coadjuvants. We only want to use natural products and plant-based products. So we have to check all of these requirements. All of these are studied in detail, and we select this set of natural products. And we combined them according to different chemical characteristics and also odorant characteristics, and using, for example, the peels of tangerine, or also some pomace for Portuguese varieties that are obtained for as byproducts of the winemaking process. And we use and select this combination of these different products. And right now we have 5 types of formulations. But how can we organize these powders to have something that may be easily used by patients? Powder, it's not a good idea. So we have to think about solutions to do something user-friendly for the patients. So we test several solutions. And right now we decided to prepare these discs with specific size and shape. For example, the superficial area, it's very, very important to promote the releasing of the appropriate amount of these odorant molecules. And we also have to optimize all of these parameters to have some discs with that be good to be used over the time, at minimum for 6 months, because it's the time that we think it's enough for this training and the recovery process. And we have to optimize also the pressing or all of these parameters. And we also need to study in detail the compounds released from these discs, because as I report in the first slides, we know that there are some specific receptors in our epithelium system, in our nasal cavity. And there are some specificity between the odorant molecules and the receptors. And we need to know what type of molecules are released from these discs and what are more efficient than others on this recovery process, or if this strategy to have a wide range of chemical structures is the best solution. So we have to check this type of efficiency, and it's important to study in detail all the molecules released from these disks. There are here some information of the major components, but we study in detail all the chemicals released from the disks. We also work in collaboration with a group from design, because we also need a packaging for these disks, a packaging that may be attractive, but also be simple to use, and also to preserve these disks, preserve for light exposure, for the humidity. So we have to control several parameters, and the idea is also to use paper, not plastic, and we have to try several options, and right now we have this option, the final option that it's now available to be tested with the different patients. So in summary, we found this opportunity related with this persistent olfactory dysfunction related with COVID-19, and use our creativity, our science and heart, and we create a multidisciplinary team, a team from natural products chemistry, from aroma chemistry, also from design, also from psychology, because and also a team from the Hospital of Aveiro. This group of psychology and also in combination with the medical team are very, very important to design the clinical trial, and also to evaluate and to help in the recuperation of the patients, because these dysfunctions are has a very huge impact in the quality of the life of the patients, namely in the diet. And right now you create this kit on the next weeks, at the next week, in 2 weeks, I don't know exactly when, but we are waiting for a lot of bureaucracies to start with this clinical trial. And our work attracted the media, what is very, very important, because on the last days I have been contacted with people from Porto, Lisbon, Algarve, from different locations that want to enter in this clinical trial. And it's very, very important for us, because we need a big group to test the efficiency, and also to evaluate several things related to the olfactory response, and how we can change or not this first model. I want to thank the team, the different teams from the University of Aveiro, also for the Centro Hospitalar Baixo Boga, and also I also to thank SOGRAP for different types of supports, namely the financial support of this project.
Thank you for this excellent transdisciplinary work, and congratulations to achieve this point. And now we are waiting for the clinical trials to have good results.
Yeah.
Thank you very much.
Okay, thank you.
Next one, Liliana. Yeah. No, now it's Liliana. Oh. Ah.
É a síntese. Helena Souza, a síntese.
Posso mexer aqui no rosto?
Pode ser o som da sala, ou som para casa, vem para aqui.
Aqui, na maior parte deles.
So, hello everyone in person, everyone online. My name is Liliana. I am here as member of the research unit Synthesis. Well, in fact, now it is the associate laboratory HYSIS. Within Synthesis, I'm a member of the Aging C group. We mostly research on aging, for sure, chronic disease and aging, formal and informal caregiving, and centenarian. So within this group, and since the start of the pandemic, many of us have performed research in this area. We chose to present this talk here, this research here, because it also brings together some form of arts. So this work is co-authored by Leah, who is also member of Synthesis, and by two great master students, Sophia and Caroline. This talk is entitled Eyes on the Pandemic, Photo Voice Reports from Frontline Social Gerontological Professionals working in residential care facilities. So, as everybody knows, during March 2020, we had the first COVID case, the first lockdown, and the first outbreak in a residential care facility. And data were showing that people aged 80+ years old had an overall rate mortality 5 times superior to the general population. So this has put frontline social gerontological professionals in the eyes of the pandemic. Of course, we wanted to launch this a kind of program to follow up this situation, but we were taken by surprise. So we launched this program, Eyes on the Pandemic, around 1 year after that first stage. So this was launched after around 1 year of the pandemic, during the second lockdown, and when the vaccination of the older persons and health professionals was starting. What we wanted, our goal, is to identify these professionals' experiences, lessons learned, and the future perspectives. We are also maintaining these participants as a panel that we are following up while it is important, relevant, while this pandemic is going on. So we use this photo voice methodology, which is a participatory action research method. And well, it brings photos and the voices of those who taken the photos. It brings those photos and those voices together. It evolves in 3 stages, so preparation, to define objectives and recruit participants, and then action. Action is taken in group sections. We did 5. So first one, just to present, to introduce everyone, to introduce the program, to launch the topic that will be photographed until the next section. And in this case, the topic was difficulty. So then between sessions, the participants take photos they think can reveal what are they feeling and they experiencing. And in the next session, they share the photos, they bring their narratives, we do a summary of the main findings, and we launch the second topic, which was lessons learned. In the next session, we launched the other topic, which was future perspectives. And in the last session, we decided with the participants the best way to disseminate the findings and also how was the best way to do that. So then we have the third phase of this method, which is finalization. That's what I'm doing here. Also, it's data analysis and dissemination. And we are going to continue with the panel with the first follow-up in September.
So we had 13 participants, 63 photographs, and 50 pages of transcriptions, and well, many hours of work during the second lockdown. The main findings that I'm going to show with pictures reveal that our participants one of the main experiences they had was finding balance between professional and personal life. Well, all these pictures were taken by the participants, so I just choose some with them. So finding balance between professional and personal life, because we all know many people have to stay at home with children, so less staff in the residential care facilities. There were members of the staff in quarantine, so less staff to respond to the needs. They were trying to find balance with the budget. These institutions operate with low budget, and during the pandemic, we need more materials, masks, protection equipments, all those things to perform disinfection. So budget balancing the protection of the older persons. So they were trying to protect older persons from being infected, but at the same time trying to maintain some well-being in their lives. And of course, they were finding balance in fear of being themselves infected, fear of taking the virus home, fear of taking the virus to work, and trying to balance this with maintaining a good job performance and well-being at home. The other topic mentioned by our participants was the need they had to reinvent intervention. So usually we talk with the others, we talk and we touch or we hug, but with social distance and with all the equipments that we were using, such as the individual protection equipment and the masks. And older people have their capability of listening impaired usually, so communication was made mainly by the eyes. So affection and messages were sent with the eyes. And this was a main change in their professional lives. Of course, there were less group activities and more digital activities, and contacts with the relatives were made by phone calls, video calls. Teamwork became a pillar of work. We teach every time that teamwork is the best way to work, but in institutions, it is typical to organize the work in tasks. But during the pandemic, there were more tasks to perform and usually less persons to perform the tasks. So everyone had to help everyone performing all the tasks that were needed in the institutions, and teamwork was the solution. Other point that was emphasized by the participants was the older persons and their relatives' resilience. So we know that older persons in residential care facilities were for a long time isolated. So they had to be very resilient to maintain some well-being while facing loneliness and isolation. And relatives also had to be resilient to live with just some phone calls or video calls. And in particular, I like that picture of that man at the window. It's one of my favorites. That man was visiting his wife, who was in a residential care facility. She was bedridden, so he couldn't go in, so he could go to the window, and as you can see, he's smiling with his eyes to her wife. So relatives were very creative in organizing ways to make them self-present and to visit between commas their relatives that were in the residential care facilities. And at a certain point, the curtain of hugs, someone invented it, and it was a way to give hugs in safety. It was very important for many people. Our participants told us that they are with their eyes in the future, with hope that things calm down. They know that the pandemic is not going to end today or tomorrow, but they hope that things calm down. Well, this was done in February. Now we know that it's not calming down, since many residential care facilities are back with isolation, but they were hoping that things calm down, and they know they are going to face uncertainty for a long period. But they also know that they have the strength and the growth to respond to the needs. So this method gives us a direct access to the experiences of these frontline persons who are not health professionals, so are not so trained as health professionals to manage these kind of situations. They reported personal and professional growth, new gerontological strategies of intervention, and the need to do whatever is possible to recover older persons in terms of cognition, mobility, and well-being. Overall, I think I can say that this has been a period of finding balance with lots of resilience and lots of reinvention of old strategies. So, thank you. As I told, we will keep our eyes in the pandemic with this panel of professionals. Thank you.
Real life study. Also, in addition to that, I would say that the old people has less expertise in the using mobile phones and teleconferences and so on. Well, thank you very much. Thank you. Next one now, Danielle. From Ivy, right?
Hello, good afternoon, everyone. I would like to start by thanking for the opportunity of being here today, presenting the research from the group I supervise at the Institute of Biomedicine. And as you can see by the title of my talk, we work with viruses directly. We are virologists, and we are mainly interested on the interactions that different viruses establish with the cells they infect, with their host cells. And why are we actually interested in this line of research? Because I'm not sure whether you are aware of, but most of the antiviral therapeutics, antiviral drugs that exist in the market are directed to specific viruses, or even sometimes specific viral strains, which renders them very much prone to resistance upon mutation, upon the appearance of viral mutants, as well as the emergence of new viral species, such as it happened now with the current pandemic. So when the SARS-CoV-2 appeared, we have no antiviral drug that could be strong enough to react against this virus. An antiviral drug that had been prepared against other viruses, even against viruses of the same family. So there is a clear need to discover different antiviral strategies that are able to tackle more than one virus, at least different viruses of the same family or different strains, but at least more than one virus. And we believe that performing fundamental research on by investigating the interactions that viruses have with their host cells, interactions with specific cell components that are used by different viruses, so similar mechanisms shared by different viruses, may take us to the development of such kind of antiviral strategies. So the viruses interact with their host cells in many different ways. In the scheme here, you can see, the image is not really clear as I see it here in the screen, but okay. When a virus enters the cell, its main objective is to multiply, to create many different copies of its own, which can then spread to the neighboring cells, the other cells of the organism, and spread to other individuals. But throughout this passage in one single cell, the virus completely manipulates the cell metabolism, the cellular mechanisms to its own benefit. It kind of hijacks the cell as a factory to make more of its copies of its own. But of course, the cell knows that and reacts strongly against it through the antiviral immune response. So basically, the cell is able to recognize different components of the virus that it infects. For example, as the viral genome, as here shown by the recognition of viral RNA or viral DNA, depending on the kind of virus that infects the cell. And then the cell starts a series of events that end with the production of certain proteins, compounds, which will act in the cell and in other cells, warning the whole organism for the presence of the viral infection. In our lab, we study different viruses, and in different aspects of the virus-host cell interactions. We have currently 3 main projects going on. One of it is financed by the FCT, and it involves the study of the role of the intracellular organelles, so intracellular, the host cell components, and its role on the antiviral immune response and on the viral propagation and virus particle formation. We have another project that just started, which is a European twinning project, which we coordinate together with Ana Soares from IBMed as well. And here we study the modifications of the host cell RNA upon viral infection, and what is the role of these modifications in the virus and in the antiviral immune response. And then the third one, which is actually the one I'm shortly going to talk about today, is the interplay between different viruses and the cellular proteostasis. And what is actually cellular proteostasis? It can be defined very in short summary as the control of protein synthesis, degradation, folding, basically the protein control in the cell. And it is known there are different mechanisms involved in proteostasis, and viruses are known to heavily influence these mechanisms. However, one of the hallmarks of deregulation of cellular proteostasis by stress is the appearance of protein aggregates in the cytoplasm. And not much is known about the viral infections, which are clearly big stresses in the cellular proteostasis and specifically in protein aggregation. So we decided to start investigating this. And for that, we used cells infected with the influenza A virus, more specifically a strain called PR8. Influenza virus is the virus that causes the flu. And for that, we infect the cells, infect lung cells with these viruses, and collect cells at different time points, which represent specific stages of this virus life cycle. So we call a virus life cycle from the beginning the virus enters up to the moment that it produces new virus particles. So for example, if we collect the cell at 4 hours post-infection, we know that the viral genome is multiplying. If we collect it at 8 hours post-infection, we know that the viral proteins are being produced, and it eventually all will get together at about 12, 16 hours post-infection, forming the new viruses that come out to the cell medium. And what we found out was that at 8 hours post-infection, so at the time point where the viral proteins are being produced, there is an increase in protein aggregation in the cell. We wanted to actually look at what was happening in the cell itself, and we did so by confocal microscopy, by fluorescence confocal microscopy, and we were able to pinpoint specific foci in the cell where this protein were aggregating, 2, 3, 4 foci, depending on the cell, which localized mainly near the nucleus, in the perinuclear area. So at this point, we knew, we found out something new. The virus infected the cell, it induced protein aggregation, but we didn't know if this was important at all for the virus or the cell. Maybe it was just a simple artifact caused by the stress of the viral infection. So to find out whether these protein aggregates were important or not, we had to be able to dismantle them, or at least inhibit its formation. And that was the point where we got in contact with the lab of Professor Artur Silva, more specifically with Elio Albuquerque, who have developed a compound which was able to disaggregate protein aggregates in cells. So the first thing we had to do, of course, was to check whether this compound was acting towards our viral-induced aggregates. And we found out it was. In the presence of these compounds, we saw a decrease of more than 50% of the amount of protein aggregates in the cells. So we knew that this compound was actually working. Our aggregates were less and smaller. So we wanted to see what was the effect of that inhibition of protein aggregate formation in the virus themselves. So for that, we quantified the number of virus particles that come out of a cell upon one cycle of infection. And we were actually quite surprised and glad to observe that in the presence of this compound, there is a decrease to about half of the viruses produced by the cells. So we not only were able to show with this that the formation of those protein aggregates was important for the virus, was not just by chance, not just an artifact, but also that this specific compound has quite an interesting antiviral effect. We were also able to pinpoint where in the virus life cycle this compound was acting, where it had a higher, stronger effect, and we found out that it was exactly at the same time point where the protein aggregates were being formed. But again, as I mentioned in the beginning, the cells are very smart and they know what's happening. So perhaps the effect of this compound was not at the level of protein aggregation, at the level of a direct interaction with the virus life cycle, but perhaps its antiviral effect was related to help it was giving to the cell, so boosting the immune response of the cell. So we went to check whether that happened, and we found out that it did not happen. It didn't have any effect on the antiviral immune response. Once again, supporting our theory that this compound was inhibiting the formation of the protein aggregates and hence helping the virus on that way. So with this project, we found out not only a new mechanism, a new important step within the virus life cycle that hadn't been shown before, the formation of these protein aggregates, which seem to be quite important for the virus particle formation, for the correct formation of the virus particles. But also we showed by controlling protein aggregation and cellular proteostasis, we may be able to control the virus somehow. And this may be the basis of a potential development of an antiviral strategy or therapy against this type of virus that cause protein aggregation. So up to now, we've only experienced this with influenza A virus, but we are currently investigating also the SARS-CoV-2 and the hepatitis C virus. And also this showed us that perhaps a compound, this one or similar to this one, may also act as a nice and potent and who knows, broad spectrum antiviral therapy. So I would like to thank the members of my lab and all the collaborators that help us with all the projects we are developing at the moment, and thank you for your attention.
Thank you, Daniela. I hope that in the near future we have a vaccine that can help to all. Thank you very much. So we are finishing our first day of the Research Summit, and now we need to do here some changes in terms of computer. And now I will call here our rector to say some words to our minister, Marta Temido. Paul, please.
Good afternoon, everybody. And my first words would be to thank our Minister of Health, Marta Tmid, for her presence here. We all know that the job of being a Minister of Health is a very, very demanding one. And in present times, it's really a massive task. We are very pleased that you have found time in your agenda to be here with us in this event. And in the present pandemic situation, that effort is even more valuable. Thank you, Minister, for your presence. As for the session, I give the floor back to Artur, and I think the word is yours now.
Yes. Please, Minister.
Muito obrigada a todos, muito boa tarde. É um prazer estar nesta sessão, ainda que desta forma a que hoje todos nos habituámos a comunicar. O meu cumprimento inicial vai, obviamente, para a Universidade de Aveiro, para a sua capacidade de inovação e de criar ciência, de fazer ciência com utilidade e relevância na vida das pessoas. Quero cumprimentar o Sr. Reitor e todos os presentes e esta iniciativa, hoje tão bem enquadrada em termos do tema que nos propõe. A ciência está na ordem do dia e entrou, em definitivo, na casa dos portugueses. Nunca tantas pessoas fora da comunidade científica falaram sobre ciência, nunca circularam tantos dados tão rapidamente, nunca as metodologias de investigação foram tão discutidas nos prime times televisivos e nos vários meios de comunicação social. Nunca talvez os cientistas tenham sido tão requisitados para falar em meios de comunicação social que se dirigem ao grande público, a um público relativamente indiferenciado. E isto deve-se a um vírus e a uma pandemia, que é hoje uma emergência de saúde pública internacional. Infelizmente, é um extraordinário feito da humanidade que tenha aparecido uma doença nova, uma pandemia, e que num espaço de tempo tão curto tenha sido possível investigar, descobrir, produzir e administrar em segurança vacinas contra a Covid-19. A ciência ao serviço da saúde, a ciência ao serviço da humanidade, a ciência como a nossa melhor aposta para ganhar o futuro, para recuperar o futuro, diria eu. Algo com que todos temos lidado menos bem no mundo cá fora é com a dúvida inerente ao processo científico, com a incerteza, com as interrogações, com as conclusões variadas de estudos e com os resultados variados de processos de investigação distintos. É da colocação das hipóteses que nascem as descobertas, são precisos muitos fracassos, todos o sabemos, para ter um sucesso e nós não podemos mesmo sucumbir, deixar-nos vencer por aquilo que é a tentação que de vez em quando vai dando sinais de aliar com os que escolhem a desinformação e de alinhar com aqueles que escolhem descredibilizar ou fragilizar a ciência. Estamos hoje num momento de charneira, aquilo que os nossos espíritos têm designado como momento de transição entre um fenómeno novo para o qual não havia qualquer resposta, a não ser medidas não farmacológicas de fechamento da sociedade, quase que à semelhança daquilo que eram as soluções disponíveis desde tempos remotos, desde a Idade Média, e um plano de vacinação, campanhas de vacinação, que são o nosso melhor aliado para ultrapassar a pandemia, para a vencer. E por isso, minhas senhoras e meus senhores, penso que é hoje incontestada a relevância da ciência e do seu papel naquilo que é um sistema de saúde. Um sistema de saúde moderno e com instrumentos de combate àquilo que são emergências de novas ameaças. Não só sob o ponto de vista daquilo que é tecnologia em saúde, para ajudar a combater doenças novas, mas também sob o ponto de vista igualmente importante e tão debatido nos últimos tempos, daquilo que é o processo científico para chegar à opção de desenho de políticas públicas. É evidente que para o Serviço Nacional de Saúde, os profissionais de saúde e a sua ligação às universidades, às escolas, aos processos de conhecimento organizados, disciplinados, sistematizados, é já uma aprendizagem que vem de bancos das escolas, mas também é verdade que nós continuamos a ter ainda grandes dificuldades naquilo que é a translação entre a investigação clínica e a prestação de cuidados de saúde. E é cada vez mais uma realidade que é por aqui que temos que caminhar, fortalecendo os laços entre a academia, a saúde e também a economia. Se há algo que aprendemos com esta pandemia é que vivemos numa sociedade profundamente interdependente e interligada, onde todas as áreas têm um contributo a dar, um papel a desempenhar para ajudar a fortalecer as respostas que a comunidade precisa em momentos particularmente difíceis. E entre as inúmeras respostas que retiramos desta pandemia, tornou-se evidente também a importância do papel da ciência nas respostas aos desafios em saúde e às necessidades dos cidadãos, bem como na busca de evidência necessária enquanto suporte e garantia do desenvolvimento de produtos seguros, eficazes e de qualidade. E poderia falar desde dispositivos médicos relativamente simples, mas com os quais não estávamos habilitados no início desta pandemia, até equipamentos, dispositivos médicos muitíssimo complexos, sofisticados, como ventiladores. Isto convoca-nos também a novos processos de avaliação daquilo que disponibilizamos aos nossos concidadãos, daquilo que disponibilizamos no mercado e à necessidade de, como país, robustecermos a nossa capacidade, por exemplo, em termos de organismos que em rede assumam essa competência de validação, certificação, aprovação de tecnologias, sobretudo num contexto europeu, onde todos partilhamos regras e princípios dos quais não estamos dispostos a prescindir, e onde o papel da academia e a independência que é reconhecida à academia tem uma função essencial para que quem produz cuidados de saúde possa operar de uma forma mais confiante e segura. Tal como o mundo mudou nos últimos meses, também toda a sociedade se mobilizou para combater a pandemia e para encontrar novas formas de produzir bens indispensáveis a todos e de criar cuidados de saúde e criar valor económico, criar riqueza. E é nesta encruzilhada, nesta transição, que nos encontramos com uma vontade indomável de continuar a caminhar em frente, recorrendo à ciência como a nossa trave mestra daquilo que é a abordagem da construção do futuro, seja em termos de soluções como medicamentos ou dispositivos médicos, seja em termos de técnicas inovadoras de prestação de cuidados, seja em termos de desenvolvimento de estratégias de políticas públicas de saúde, e a Universidade de Aveiro é também nesta área uma escola que nos ajudem a decidir melhor e também a comunicar melhor neste mundo tão turbulento. Como a quarta vaga que estamos a viver hoje também o demonstra, a batalha não está ganha e exige de todos cuidados, atenção, comportamentos que sejam responsáveis, que sejam informados. As vacinas defenderam os mais frágeis das manifestações mais graves da doença e mesmo da morte, mas estamos ainda a trilhar um caminho que ainda tem muito chão para andar. A vacina que a ciência nos deu e tantos outros apetrechos, artefactos com que hoje enfrentamos melhor esta pandemia são grandes avanços, é um grande avanço, mas também por causa disso temos a obrigação de fazer a nossa parte e evitar as cadeias de transmissão e de assim possibilitar também o desenvolvimento do conhecimento, porque o conhecimento leva tempo e é esse tempo que a nossa responsabilidade individual pode ser o contributo para este processo de construção conjunta e de reforço das nossas respostas coletivas a esta ameaça de saúde pública internacional, para a qual nenhum de nós estava preparado, embora ela fosse mais do que previsível, prevista, e que certamente não será a última face àquilo que são as alterações em que nos movemos, em termos de contexto designadamente ambiental, e que, portanto, ganharemos em conhecer melhor e em estar mais preparados para enfrentar de uma próxima vez que se abata sobre nós uma situação de emergência sanitária internacional como esta que enfrentamos. Por isso, a minha última palavra é para agradecer genuinamente o trabalho de todos aqueles que fazem investigação e que com a sua investigação, com o seu estudo, com o seu método, com os seus dados, com o seu trabalho de dados, com a sua capacidade analítica, o transformam em conhecimento e o partilham com a sociedade no sentido de criar valor e no sentido de fazer aquilo que me parece que é, no essencial, o papel de uma universidade do futuro. Ser relevante não só pelas publicações que tem, pelos doutores que a prestigiam, mas ser também relevante pelos problemas sociais que ajuda a resolver. A Universidade de Aveiro tem múltiplos exemplos de bons exemplos, situações em que permitiu que isso acontecesse e é, portanto, um orgulho poder estar aqui, ainda que de uma forma muito simples e muito cirúrgica, a partilhar este agradecimento em nome dos profissionais de saúde e dos prestadores de serviços de saúde, com quem nos ajuda a conhecer melhor o mundo e, portanto, a atuar melhor sobre ele. Muito obrigada.
Obrigado, Sra. Ministra. Esperando que numa próxima oportunidade esteja connosco e estejamos nós menos mascarados do que estamos hoje, que aqui estamos aqui pondo máscara e tirando máscara. Muito obrigado pela sua contribuição.
Muito obrigado também. Muito boa tarde.
Well, only to say thank you very much for all of you that stay with us here in the auditorium and also through the Zoom and through the YouTube. I think that at the end of the day, I'm happy because we have a lot of problems in terms of sound well informatics, but I think that we tried and we reached the objective that we wanted. So thank you very much, and applause for all of us.